would be in an echelon form. It wouldn't be in reduced row echelon form. Okay. What I want to do is I want to find the inverse of matrix A. So I want to find the culmination of all the operations on A, or that I would take on A, to get it into reduced row echelon form or to the identity matrix, and just do the reverse of that. All right, so apply all that to the identity matrix. All right, so whatever I do to A, I'm going to do to I. So let's take a look. So I'm going to row reduce this. So little negative 3R1 plus R2. Get us started. I think. And then we'll do, let's see here, a 2 R2 plus R1. Oh, I want to do that in red. So that would be negative 6 plus 1 is negative 5. 2. Again, our goal is to get the matrix A down to reduced row echelon form or to the identity matrix. So it looks like all I have to do to get there would be to take row 2 and negate it. And so therefore, the inverse of A would be negative 5, 2, 3, negative 1. Very simple, very easy, with a 2 by 2 matrix. Too many people fall asleep when I'm teaching, though. It'll be a 7 by 7 matrix on the test. All right. So I'll put a star on this one. I'm just having a moment of internal debate where it's like, do we prove the rule, the shortcut rule, or do we just kind of let that one go for now? I get an idea. Example. There we go. With that going up there. So I'll take that as a typo. Okay. But basically, it's just row operations that should get you from this down to the identity matrix, and therefore the identity matrix should end up being this. Now, it might not take that beautiful looking form, but it should have some similarity to it. Actually, it might be a god-awful mess. We'll see. But it seems like a fun exercise for tomorrow. Yeah, so you could use the shortcut rule, but my feeling on shortcut rules, like the matrix multiplication, is the real shortcut is what I already showed you on the calculator. Right? So you should really be practicing how to do it with the row echelon, reduced row echelon technique, because the calculator is your ultimate shortcut. I don't think I ever really liked example 3. I'm still kind of deciding on what purpose it serves, so we can get rid of that. They're kind of lame word problems. I mean, they're doable, I guess. Alright, well, we'll do it. Alright, so it's using inverse matrices in order to make a determination of the solution to the matrix equation AX equals B. Now, we learned previously that there is no matrix division. There's no dividing both sides. But there's no reason why you can't multiply both sides by the inverse of a matrix, right? Because the product of a matrix and its inverse is the identity matrix. That's the whole point of the process, right? So if I were to multiply both sides of this equation by the inverse of A, I would get the identity matrix multiplied by X on the left, and on the right it would be the inverse of A multiplied by B. So essentially it would look something like this. Let me actually zoom. I'll go 300. So you'd have A multiplied by the inverse of A times X equals the inverse of A times X. And then the identity matrix I multiplied by X equals, oh, sorry, B on the right-hand side. And then a definition of an identity would be that object maintains its identity through multiplication, but I would also add to that only when it makes sense to, right? So this is only equal to X when it makes sense for it to be equal to X, which would be the case where the dimensions of the two matrices dictate that that multiplication is possible, right? So when multiplication is possible, I times X would be equal to X, which would give you the relation that X equals inverse of A multiplied by B, right? So it's an important thing to keep in mind, because if I gave you something like, I don't know, a 5 by, identity matrix 3 by 3, and then an X matrix of like 7 by 1, so the vector with 7 rows, that wouldn't carry through multiplication, so it wouldn't make sense, and so therefore this relationship wouldn't hold, right? So it's not in all cases, but it's in most cases, in any contextual situation that I give you, obviously. All right, so something relatively simple. Megan paid $39 for 3 pounds of pistachios, and 2 pounds of cashews. Tanya paid $23 for 2 pounds of pistachios and 1 pound of cashews. As a system of equation where X represents the cost of a pound of pistachios, and y represents the cost of a pound of cashew. So 2y equals 59. So 2x plus y equals 23. And again, you can do this through simple algebra, but that's not the point. All right, so 3, 2, 2, 1. That's y equals 39, 23. All right, so this is in the form of ax equals b. So I need the inverse of a. So I'll do a quick negative 2/3 R1 plus R2. So 0 out the first entry in the bottom row. Let's see, that's negative 4/3 plus 1, so negative 1/3. Then we're looking at negative 2/3, 1. All right, so let me multiply the second row by negative 3. Negative 2 R2 plus R1. Blue. Then, barring any terrible mistake, 1/3 on R1. And so we have our, I'll double check, just 3, 2, 2, 1. Oh, good. Shocking. All right, so if I find the product of my inverse matrix and my B vector, 39, 23, the quote-unquote X, and 39 plus 46 is going to be, what, 13? Then 78 minus 69. So 9. 13 to 9. So 13 pounds of pistachios and 9 pounds of cashews. Do the quick checkaroo here. I'm going to store this into matrix A. Matrix B, I need 2. 39, 23. So matrix A times matrix B. If it doesn't have the proper dimensions, it won't let me carry out the multiplication. 7 and 9. Okay, wonderful. Oh yeah, negative 39 plus 46. Yeah. Change the blue too, because it's not 49, it's 46. All right, so put a star on the second one, which is, I think, even easier in terms of the setup, but it's really the inverse process and the multiplication component that you want to practice with. So.